All right, let's jump right in. We're going to talk about what happens when you smash two of the most powerful, and let's be honest, most hyped technologies together: artificial intelligence and quantum computing. The result is quantum machine learning, or QML. And I think you'll find the real story here is, well, it's not what you'd expect.
You know, at the heart of all the buzz, all the excitement, is this one huge question. What if our AI models, the ones that are already changing our world, could tap into the bizarre, almost magical rules of quantum mechanics? What if they could become exponentially more powerful? This is the grand promise, the vision that's fueling billions in research. And we're not talking about small improvements here. The potential applications are just staggering. Think about discovering new drugs for diseases we currently call undruggable, or designing brand new materials atom by atom, or completely revolutionizing financial markets. These are the kinds of problems so ridiculously complex that even our best supercomputers today would need literally longer than the age of the universe to solve them.
Okay, but here is where the story takes a really fascinating turn. This whole thing isn't just about quantum computers making AI better, it's actually a two-way street, a symbiotic relationship. And the surprising truth is that one direction of that street is way more important and way more practical today than the other. You can really split the entire field into these two big ideas. On one side, you've got the sci-fi vision, quantum for AI. That's all about using these new quantum machines to supercharge machine learning. But then, on the other side, you have the work that's actually making it all possible right now, AI for quantum. And that's about using the AI we already have to actually build and control the quantum computers themselves.
So let's start with that side of the street, the one that gets less of the hype, but is frankly the bedrock of this entire field. This is where classical AI is the unsung hero, the technology that's making quantum computing even a remote possibility. And why do we need AI's help so badly? Because today's quantum hardware is, well, to put it nicely, it's delicate. We're living in what scientists call the NISQ era. That stands for Noisy Intermediate Scale Quantum, and noisy is the key word there. These machines are unbelievably sensitive. The slightest vibration, a tiny change in temperature, it can create a constant stream of errors that just wrecks any calculation. This is where classical machine learning is really coming to the rescue. It's pretty amazing, actually. AI agents are learning how to send the perfect little microwave pulses to control the qubits. Then you have other machine learning models that are getting crazy good at recognizing the patterns of that quantum noise, and then they help implement error correction strategies, like on the fly. Without this AI supervision, these quantum machines would just be too chaotic to be useful for anything.
Okay, so now let's flip the coin. Now that AI is helping us build better, more stable quantum computers, we can finally start to explore that grand vision we talked about earlier, using the unique power of quantum mechanics to give AI brand new capabilities.
To get how this works, you've got to meet the star of the show, the qubit. Now, you know a regular bit. In your phone or laptop, it can be a 0 or a 1. That's it. A qubit, though, it can be a 0, a 1, or kind of sort of both at the exact same time. The best analogy is a spinning coin. While it's in the air before it lands, it's both heads and tails at once. That mind-bending property is called superposition.
Superposition is what lets a quantum computer explore a vast number of possibilities all at once. But the real magic, the secret sauce, kicks in when you add a second quantum trick, entanglement. This is what Einstein famously called spooky action at a distance. It's where you can link two qubits together so their fates are intertwined. Whatever happens to one instantly affects the other, even if they're miles apart. And when you combine these two things, that's where the exponential power comes from.
And hey, this isn't just theory anymore. We're starting to see early but really promising breakthroughs. Researchers have used QML to look at potential drugs for the KRAS protein, a really notorious cancer target. Big banks like HSBC are already using it to tackle super complex risk modeling, and companies like DHL are exploring how it could solve these insane logistics problems. So for very specific, very hard problems, that quantum advantage is slowly starting to peek through.
All right, so we've seen how AI is foundational, and we've seen the futuristic promise of quantum. But where do things actually stand right now, today? Let's get real for a minute and separate the practical from the theoretical. This little chart tells the whole story, doesn't it? Classical machine learning, it's mature, it's everywhere. AI for quantum, that foundational stuff we talked about, it's delivering high value in labs right now. But pure quantum ML, that futuristic part, you can see it's still in the experimental phase. Its practical value today is, well, it's pretty limited, and it is extremely dependent on getting better hardware. And that's because there are still these massive physics-level hurdles we have to get over. Just getting huge amounts of data loaded into a quantum state is a huge bottleneck. It's slow and expensive. Then there's this weird problem called barren plateaus, which is basically a quantum version of the vanishing gradient problem in AI, where bigger models just stop learning. And of course, the hardware itself is still noisy and pretty limited.
So what does all this mean for the future? Well, the path forward isn't quantum versus classical. It's not a competition. It's about a deep, intelligent integration of both.
You know, for the next decade, probably longer, quantum processors are not going to replace your laptop. Think of them more like a specialized coprocessor. It's just like how a powerful GPU, a graphics card, works alongside your computer's main CPU. The GPU doesn't do everything, it just handles the really intense graphic stuff it was built for. Quantum computers will be like that, specialized accelerators for the very specific problems that they are uniquely good at solving.
So what does this look like in practice? A typical hybrid workflow is like a tag team. You start with a classical AI model to do all the heavy lifting up front, processing the data and finding the key features. Then it hands off one very specific, very hard piece of the puzzle to a small quantum circuit. Once the quantum part spits out its answer, it's fed back into the classical model to make the final call.
And this brings us to what might be the single most important strategic insight in this whole field. For all the talk about quantum-changing AI, the surprising truth is that classical machine learning is an absolute prerequisite for building a useful, scalable quantum computer. Without AI managing the hardware, the whole quantum dream just stays a dream. So, this leaves us with a final, really fascinating thought to chew on. We've just established this powerful feedback loop, right? AI makes quantum computers better, which in turn will be used to make AI better. As this cycle spins up and accelerates, what problems that we can't even imagine today will this incredible partnership finally allow us to solve?